Excuse me. Hello, everybody. So this is my first recording of going through the course materials for environmental economics. Whoa, I'm on the wrong slide. Let me go and stop. Okay, so this section that we're doing this week is on Chapter 15 on water and Chapter 10 on agriculture. So this recording is going to be on water, and there'll be a separate recording talking about agriculture. Okay, here we go. So when we're thinking about any kind of resource, right, which water obviously is, amongst other things, a resource that we use for all types of things, we can explore whether it is a renewable resource or a non-renewable resource, right? Non-renewable resource being something like oil, right, which is there is what there is in the ground, right? In any kind of meaningful time frame, there isn't going to be more produced for us to use, right? Or a renewable resource, whether that be fish in the ocean, as we've explored, or forests as they can grow, and new trees be planted. So where would water fall? Well, water is, as overall, renewable, right? As our authors of our textbook suggest, water can be characterized as a renewable resource, since it can be, they use the word reused indefinitely, but I would suggest replenished, right? That more can be, quote unquote, produced, more fresh water can be produced for us in a process that I will talk about in coming slides, as long as that resource is not severely polluted. Okay. So to think about how it's reproduced, we all have a kind of a sense of how more water comes to us, and most of it comes through precipitation. Excuse me. And thinking back to the framework that we defined in the first half of the course of stocks and flows, right? We have flows of water, right, and we have stocks of water. So the flows of water being the evaporation, so water leaving the earth, right, going into the clouds, because that's what creates the ability for the clouds to give us the precipitation, where we get new water that replenishes rivers, the stocks, replenishes the stocks, the rivers, the lakes, the aquifers, right, the places where we can have water collected that we can use. Excuse me, let me get a drink of water here. I don't know what's going on. Okay. So yeah, this hydraulic cycle is how more water is produced for us. Now, so the water resource that we have available to use, for the most part, is where the water gets collected, right? Either in the underground aquifers that we can get through wells, right, or other type of drilling into the earth to kind of pump it out. Rivers, lakes, reservoirs, etc. So in general, it is renewable, and on a coming slide, we'll explore literally how the earth produces for us, or the hydraulic cycle produces for us more fresh water each year. But we'll highlight often that, like any renewable resource, it only renews, or can renew enough to be sustainable, as long as it is not extracted beyond the maximum sustainable yield, right? Like we saw in the fishing simulation, right? We overfished, so we depleted the resource. Well, water resources, to a degree, can be depleted in the same way, right? So if we extract the water faster from, say, the aquifer or the reservoir, then it is recharged, right? Then it gets diminished, right? The stock shrinks, i.e. outflows are greater than inflows. We're extracting faster than the maximum sustainable yield, which happens periodically throughout the world, happens whenever there's a drought situation, right? But it happens very consistently in parts of China, Mexico, Pakistan, India, parts of the western United States, have been having chronic drought conditions where outflows are greater than inflows for a lot of water resources. Water is also depletable, right? And when we talk about water, the water's still there if it's polluted, right? But it's polluted to the point where we can't use it. So what we're, for most purposes, right? So for what we're looking at here is, when we're talking about the water resource, fresh water resource, right? That we can use for cooking, drinking, hygiene, etc. Well, if it's polluted, if the groundwater is polluted beyond recovery, either through sanitation getting into it, or through, say, a pipeline that carries oil breaking and basically getting into the aquifers, which many farmers and other people in the Midwest are concerned about, from pipelines coming from Canada bringing oil down. It can basically make that water unusable for virtually any purposes that we have. So it is, in that sense, can be depletable. And in very isolated cases, it can actually be non-renewable, almost like oil, where there are places, for example, in Saudi Arabia and Libya, where there are aquifers that recharge so slowly, or that they effectively don't recharge, right? The water can't seep into them to recharge them. So if we take the water out, it is effectively like taking the oil out of the ground, right? But that is the not the most common case, right? In most cases, it's renewable, although it might be depletable. Now, I never really thought about this before I honestly taught this course, but the reality is that where we get our water, right, or the part of the cycle that makes more water available, fresh water available to us every year, is effectively transferring water from the oceans to the land through the hydraulic cycle, right? So how does that work, right? Every year, water evaporates everywhere, both from lakes and streams on land, but also, and even more significantly for this process, from the oceans, and basically evaporates from the oceans and then falls, part of that evaporation falls on the land, right? So it transfers the water, the salty water, which it takes out the salts, purifies it, goes into the atmosphere, and then falls as precipitation onto land. Excuse me. To the tune of 110,000 cubic kilometers of water per year. Now that's a unit that is hard for me to put my head around, and I'll turn that. I'm going to try to, in future slides here, turn that into something a little bit more digestible, something that makes more sense. Right? How much is a cubic kilometer of water? Hard to grasp what that means, but it's a lot, right? So 110,000 cubic kilometers of water falls, right? But a lot of that evaporates, right? Goes back or flows back as groundwater, evaporates back into the atmosphere, right? So the net, right? The net amount of water that is transferred from the oceans that isn't then also evaporated back into the atmosphere is effectively 40,000 cubic kilometers of water. So that is the amount of freshwater resource that every year approximately gets regenerated to potentially use for humans, for animals, for people, for any land-dwelling creatures or living things. Right? So availability of water. Freshwater resource, again, that's our focus. We're focusing on fresh water, water that is theoretically available for drinking, hygiene, agriculture, industry, right, for human use. Now, if you think back to the documentary, The Last Drop, that we watched on the last day of class in the semester that I'm recording this before spring break, a very tiny fraction of all the water on the planet is freshwater resource, right? 0.003% of the water on Earth, right? If you think back to that documentary, by the way, if you weren't in the class and you haven't seen the documentary, it is available on Films on Demand. Just type in Last Drop and you can watch it. There they described how, most of the water that is on the Earth is in the oceans, and for a lot of the uses of water, that's not usable for us, right? We can obviously still swim in it, but can't meaningfully drink it, right? The salt, I've seen movies, I'm sure, with someone floating in a raft and basically dying of thirst despite so much water around, right? So unless it's desalinated, which is artificially, right, absent kind of the natural hydraulic cycle where it evaporates and naturally desalinates the water, right, and falls as precipitation. Very expensive process. So most of the water in the ocean is not usable, right, not a freshwater resource for drinking, hygiene, agriculture. If you try to use salt water to water plants, they will die. Of the rest of the water that is on the planet, 99% of that is not usable because it's or economically, right, not theoretically available for our use, because it is trapped in the Antarctic ice sheet and the Greenland ice sheet, or permafrost in northern Canada or Siberia, for example. Right? So in the documentary, they try to put that in perspective by saying, hey, if all the water on the planet could fill a bathtub, basically a teaspoonful is what is this theoretical freshwater resource that we could theoretically have available for use. And that 0.003% is still quite a bit of water, right? This hard to comprehend what it means, 40,000 cubic kilometers of water, which I already talked about is a transfer from the oceans to the land through evaporation, precipitation. Now, of that 40,000 cubic kilometers of water, about a third, or about 14,000 cubic kilometers per year, is what is actually economically available for use by people, right? And why is 2/3 of it not economically available for human use? Well, because we don't have a effective way to capture it, right? It either flows right back in the ocean, or it evaporates, or it goes into some place where that is a stock of water that is polluted beyond recovery, right? So only about a third of it is effectively available for us to use. That's what it means by economically, right? Although we might be able to build more reservoirs and do other ways of capturing it, only about a third of this 40,000 cubic kilometers is really available for us to use, right? In a meaningful way. Right? Now, I promised in an earlier slide that I'm going to try to kind of turn those numbers of cubic kilometers into something a little bit more meaningful. Right? So I did this a couple of years ago, so the numbers would be a little different because population has grown a bit since I did this, but we're just looking for an order of magnitude for this discussion anyway. And by the way, nothing that you need to know exactly, but just making this a little bit more meaningful. So if you take all of the water, this 14,000 cubic kilometers that every year becomes available for us to use, right, the renewable resource for us to use of water, and divide it, if it was evenly distributed, and that's a big if because it is not, but if it was evenly distributed to people around the world, that would basically translate into 2,000 cubic meters of water per year per person, which is still not so meaningful, but maybe more something you can, or at least I can wrap my head around. Almost 1,480 gallons per person. And that sounds like a lot of water available per person, right? So let's forget the distribution issues for a second. So on average, that's what's available per person. Right? The World Health Organization says that, hey, the minimum needed per person for drinking, cooking, and hygiene is 50 liters, which translates to approximately 13 gallons. Right? Now, if you read the book and talk about when areas are water abundant versus water scarce versus something in between, which is often termed water stressed, the discussion suggests that to be water abundant, right, to have enough water per person to be able to comfortably support a modern society, we need about 1,400 gallons of water available or allocated effectively per person. So the question to really understand, or one of the things to really understand, is why the heck do we need 1,400 gallons per person available for a modern society to have enough water effectively to be comfortable, when the World Health Organization says, hey, we only need 13 gallons per person, right? Why do we need more than 100 times that much per person? Right? Well, it's because a tiny fraction of the water we need is for direct cooking, drinking, and hygiene. Right? Most of the water we need is for agriculture, right, to grow the food that we eat, which we'll talk about how much crazy amounts of water that takes in the next section on agriculture. And industry. Industry uses a tremendous amount of water, although it's not nearly as obvious why, but it does. Right? So most of the water needed for us to have a modern society is for the food that we eat and the products and services that we buy. Right? So if you have less than that per person available, which many parts of the world do, right? You can be water stressed if you have a bit less than that, but the book discussion suggests that, hey, if it's half, right, of that 1,400 gallons per person, right, if it's less than 700 gallons per person available per year, that's going to start to have significant constraints on the ability to grow enough food and have enough economic activity, industry in that country. Right? Now, as was mentioned, right, this is if it was evenly distributed, we wouldn't be water stressed, right? We would be just enough that'd be water abundant, but it's not evenly distributed, right? Some regions are water scarce, right? Much of Africa, Middle East. Some and some are water stressed, right? Where there's somewhere in between. And even parts of the United States, right, is stressed, right? On the West Coast, for example. So if we go to this link here, we will see that, amongst other things, there is this chart that basically shows that parts of the world, right, most of the U.S., right, Canada, other parts of the world, a lot of the world doesn't really have a lot of water scarcity. Some areas have, which we haven't defined the distinction between this physical and economic yet, but physical water scarcity, literally there is not enough, right, or that is approaching it, right, water stressed. But then there's this huge swaths, especially sub-Saharan Africa and parts of India and China and parts of South America, that has economic water scarcity as opposed to physical water scarcity. So the next thing for us to try to understand is, what is the distinction? What does it mean for water to be economically scarce as opposed to physically scarce? Well, what it means is there hasn't been enough, or there isn't enough financial resources to develop the water resource, right? The human, institutional, there's not enough organization, not enough resources, not enough financial capital available to build the aquifer or the pumping stations and the reservoirs and the dams and the other things to be able to extract the piping, the plumbing, et cetera, to be able to make that resource available for people. Right? So if you think back to the documentary again, right, Israelis developed the water resource in that part of the world much more so than the Palestinians did. So although that part of the world does have physical water scarcity, where not enough water falls, right, to comfortably have modern society, right, grow enough food and industry. But of the water that is available, Israelis did this, right? They don't have the economic water scarcity to the extent that the Palestinians did, because they did develop the resource, whereas the Palestinians did not. And in Africa, although it might be surprising, most of their water scarcity in most parts of Africa is not because they have physical water scarcity, but it's because they have economic problems. They have the lack of investment to be able to utilize the water that is there. Here's an article, a little dated at this point, but circumstances haven't changed too much since then, that rainwater harvesting, for example, collecting the rainwater more effectively that falls, could end much of Africa's water shortages, right? So highlighting that it is more of an economic problem than a physical lack of water. Okay. So here's basically the same chart, right, that was on that other the website we went to. Now, when we think about something scarce, right? So if there's not enough of something in economics, right? Well, that means people want more than there is available. So we can think about that in terms of supply, right? We can think about that in terms of the amount of that is available, right? And we can think about that in terms of demand. So if there's a shortage, there's two ways, right? Two categories, I guess I should say, of ways to shrink that imbalance between how much people want to use or need to use and how much is available. One way is to increase the supply, and that's probably the one that we think about first. How do we increase how much water is available? Well, we can capture more, right? Build more dams and reservoirs, which is happening in many parts of the world. As that article that I pointed to in the last slide mentioned, more of that could be done in Africa because a lot of their issue is economic water scarcity. So do more rainwater harvesting. Reuse and recycle, right? So back to the documentary, The Last Drop, again, that we watched, that you can watch on Films on Demand in the library. There were places that were effectively treating, right, wastewater treatment plants, basically turning wastewater into, again, usable water. Create more, quote unquote, and I put that in quotes, right? For example, with desalination plants, right? The world has effectively, through the hydraulic cycle that we went over earlier, does desalination on a massive scale through evaporation and precipitation, but we can do it on a more of a micro scale by building plants, right, that do the same function, right? Take the salt out of the water, desalination, desalt, right? And here's an article that basically shows that Israel has been able to do that in a fairly significant degree. Now, looking into the future, or frankly in the present even, climate change is causing challenges in being able to do these types of things, to increase the supply of fresh water where there is shortages, right? Where there's not enough available. Because one of the things that we'll talk about when we get into climate change is that it is showing already happening and is expected to happen to a much larger degree, that parts of the world that are already wet, i.e. get a lot of precipitation, are expected to get more, and places that are already dry are expected to become drier, so shrinking the supply further, so exacerbating the challenges that places of the world that already have. We already talked about that. Okay. So besides increasing the supply, right, another way to deal with water scarcity, right, either economic or physical, is to decrease the demand. And I guess when we think about drought restrictions, right, when we start having a drought and they say, all right, you can't water your lawn, you can't wash your car, you can't do this, you can't do that. So decrease the demand. So how do you do that? Well, like I mentioned, water restrictions. But one of the even more, since domestic use of water, right, us at home using our water is a tiny fraction of the total water that is used, right? Far more meaningful reductions in demand for water would be more effective irrigation, right? Putting the water directly on the plants as opposed to just spraying it over the plants. And when you are doing the irrigation, right? So effective irrigation systems. Decrease demand by changing people's behavior, right? Again, that's not the biggest piece because it's not agriculture, it's not industry. But in the documentary, we watched the Get Water Wise campaign that Namibia was doing, where they were teaching students how to use less, demand less water. They were basically educating having the hydro cop go around to try to give fines, basically ways to reduce people doing things with water that weren't authorized. Another way to decrease the demand, the amount that people want to use of water, is to raise the price of water, make it more expensive for that water. Now, the reality is that many countries, including ours, subsidize water prices, right? They don't charge people the full price of the water that they're using, right? So if you get your water through a public utility, the amount you pay in your water bill, per month, per quarter, however that's billed to you, often is not covering the full cost of that water. It is being subsidized. So how does that contribute to shortages? Well, let's think about this in terms of supply and demand. This just says economists' problem with water, pricing water below cost. So, on the vertical axis, we have the price of water. On the horizontal axis, we have the amount of water available. Don't worry so much about these absolute numbers. This is just you can think of it as millions of gallons a day in some community. Right? So, anytime we have the demand for something, right, hopefully it makes sense that the higher the price is, the more we have to pay for that thing. The less the quantity is, right, the further to the left, right, that we are on this graph. So if you raise the price of water, people want to use less of it or can afford to use less of it. If you lower the price, they're going to use more of it. Now, supply goes the other way, right? So if you raise the price that is charged for water, you might even have private companies saying, hey, let's us start selling water and providing water. So the higher the price, the more incentive there is for producers to produce more of that product. And this is true not just for water, right? This is true for basically any product. So economic theory suggests, hey, a kind of often or usually a logical price is where the price at which the quantity demanded and quantity supplied are the same, where there's an intersection. Now, when I say that water prices are subsidized, right, pricing water below cost, well, you can think of that as pricing it below that equilibrium, below that price. So let's say we charge a price down here. Right? It doesn't matter exactly what these numbers are. There's no price here, but you can consider this $1 a gallon, and you consider this $2 a gallon, but however you want to think about it. But it's basically you're charging less than effectively the cost of providing that water. So how does that create a shortage? Well, at that lower price, people want to buy more based on the demand than there is available, and that's when we start diminishing the water resource. That's when we start overusing it and using it beyond the maximum sustainable yield. That's what creates the shortage. So economic theory suggests that, well, when you have a shortage created because you're pricing it too low, you can raise the price. Now, that's a way to decrease demand, and I guess I should say also it increases the supply potentially, because now there's more incentive to produce that water. You can afford to make more water. Maybe you can afford now to make a desalination plant, for example. But we're going to focus on the demand effects of raising the price. So basically, if you raise the price, there's economic incentive not to overuse it. People can't afford as much. Right? You can so one way that that's being done some places is you privatize it and you let the private company charge a price that lets them stay in business, right, where they make enough profit. But that often causes challenges and often causes a lot of angst. But so we won't worry so much about that. But charging the full price. Now, one of the problems with charging the full price, right, not subsidizing water, is for some uses, obviously, water is right behind air as far as the resource that we need most immediately to stay alive, right? So making basic amounts available to everybody often makes sense to continue to subsidize so people can afford to have enough, even provide for free, but people can afford to have enough for drinking, cooking, hygiene, for basic needs, right? But charging more for usage above that. Right? So charging more, for example, you want to water your lawn, you got to pay more. So often you can accomplish this decrease in demand without causing people not to have enough to survive by having what's called tiered water pricing. So basically where you charge different amounts, right, at for different amounts of usage. Basically, this podcast, effectively, or this recording from NPR, discusses how Santa Fe, New Mexico, dramatically cut the amount of water consumption that they had by having exactly that, right? So they charged a very low price per gallon for low amounts of usage. They charged more per gallon if you used more water, and people responded, as economists would expect, by using less water. Now, when we think about Palestine and the Palestinian-Israeli water conflict, right, one of the questions that you were asked to consider from the last drop of Films on Demand, that discussion, is it was suggested by some in that documentary, by the Israelis and by the one economist there talking about it, that Israel might, you could argue, might have more of a claim to the shared water resource that they have with the Palestinians than the Palestinians do. And what was the argument for that? What was the why they might have more of a claim? Well, Israel, as was mentioned a little while ago here in this discussion, developed the water resource, right? So they built the pumping stations, they built the infrastructure to be able to access the water that was in the aquifers, and what was mentioned in the documentary is that international water law basically is written such that if you do that, if you develop a shared water resource, if one party develops it and the other doesn't, you effectively develop a legal right to it. Right? I'm not going to worry. Don't worry so much about this private good thing. I think trying to explain that would be more confusing than it's worth. But that's the argument, right? That's the argument. The Palestinians, however, would argue that, hey, some Israelis have enough water for luxuries like filling swimming pools, where Palestinians don't have enough water, right, for necessities, and that, hey, they ought to be able to share. They ought to share. Right? So that was the argument against that, against the Israelis having more of a claim. And that's basically our water discussion. And I will make the part 2 of this section discussing agriculture next.